In the intellectual crucible of the 3rd century before the Common Era, following the world-altering campaigns of Alexander and the establishment of Hellenistic centres of learning, the cosmos itself became a subject of intense rational scrutiny. Within this fervent environment, a figure of extraordinary vision, Aristarchus of Samos, produced a treatise that stands as a foundational monument in the history of science. His sole surviving work, On the Sizes and Distances of the Sun and Moon, represents a conceptual revolution. It is an artifact of pure reason, a demonstration that the architecture of the heavens was amenable to the rigorous language of geometry. The enduring significance of this text resides less in its famously inaccurate numerical conclusions and more in its profound methodological leap. Aristarchus bequeathed to posterity a rational, repeatable process for measuring the cosmos, an intellectual framework whose brilliance and audacity far outshine the empirical limitations of its age. This treatise marks the very birth of mathematical astronomy, the moment when humanity first attempted to grasp the scale of its celestial neighbourhood with the tools of logic and observation. The intellectual landscape from which Aristarchus emerged was one dominated by philosophical speculation and elegant, yet unscaled, geometric models. Predecessors like Anaxagoras of Clazomenae had offered provocative materialist conceptions, famously declaring the sun a fiery mass larger than the Peloponnesian Peninsula, a statement that was more a challenge to theological orthodoxy than a scientific measurement. Later, the great geometer Eudoxus of Cnidus, a contemporary of Plato, had devised an intricate system of concentric spheres to account for the perplexing motions of the planets. His model was a triumph of descriptive geometry, designed to save the phenomena by reproducing celestial movements, yet it remained a purely relational architecture. It described the choreography of the sky without providing any sense of its depth or dimension. The cosmos of Eudoxus was a celestial ballet without a stage. Aristarchus confronted this fundamental absence. His ambition was to transcend the qualitative descriptions of his forebears, to move beyond the questions of what and why to the far more challenging inquiries of how large and how far. He sought to apply a metric to the heavens. For this undertaking, the intellectual toolkit of his era had recently been perfected. The axiomatic and deductive methodology enshrined in Euclid's Elements provided the template. On the Sizes and Distances is, in its very structure, a Euclidean proof translated to the grandest possible scale, applying the unyielding logic of geometry to the physical reality of the sun, moon. The treatise unfolds as a series of geometric propositions derived from a small set of foundational hypotheses. The first and most celebrated argument tackles the relative distances of the sun and moon. Aristarchus begins with a simple, yet profound, observation of the moon-at dichotomy, the precise moment of its half or phase when the terminator, the line separating the illuminated and dark hemispheres, appears as a straight line to an observer on Earth. He posited that at this instant the Earth, moon, and sun must form a vast right-angled triangle in space, with the right angle located at the moon. The line from the moon to the sun and the line from the moon to the Earth are the two perpendicular sides of this cosmic triangle. An observer on Earth can, in principle, measure the angle at their own vertex of this triangle, the angle between the direction to the moon and the direction to the sun. Aristarchus reported a value for this angle of 87 degrees. From this single observation, the entire scale of the local cosmos could be unlocked. The ratio of the Earth-Moon distance to the Earth-Sun distance is equivalent to the cosine of this 87-degree angle, or, using the complementary angle, the sine of 3 degrees. In an age preceding formal trigonometry tables, Aristarchus employed a powerful set of geometric inequalities, a method familiar to Archimedes, to bound the value of this ratio. His calculations led him to Proposition 7. The distance of the sun from the Earth is greater than 18 times, but less than 20 times, the distance of the moon from the Earth. The specific numerical result was secondary to the sheer power of the method. For the first time, a sound, logical chain of reasoning, anchored to an observable phenomenon, had produced a concrete ratio for the fundamental distances of the solar system. With a cosmic yardstick in hand, Aristarchus proceeded to determine the relative sizes of these celestial bodies. Here, another piece of elegant observational evidence came into play: the remarkable coincidence of a total solar eclipse. He knew, as did his contemporaries, that during such an event, the tiny disk of the moon almost perfectly obscures the colossal disk of the sun. This implies that both bodies subtend the same angle in the sky as viewed from Earth. His second hypothesis stated that the moon and sun have an apparent angular diameter of 2 degrees, a rough overestimation but one that served his geometric purpose. The logic that follows is inescapable. If two objects at different distances appear to be the same size, their true diameters must be in direct proportion to their respective distances. Having already established that the sun is approximately 19 times farther away than the moon, it followed directly that the sun's true diameter must also be approximately 19 times greater than the moon's diameter. This conclusion, derived from straightforward geometric principles, was staggering. It transformed the sun from a large celestial fire into a body of truly immense proportions, dwarfing the moon in a way that mere philosophical conjecture never could. The sun was a physical object of almost unimaginable size, a realization that would have profound, if unstated, implications for its place in the cosmic. The final and most geometrically complex portion of the treatise endeavours to relate the sizes of the sun and moon to the size of the earth itself. To achieve this, Aristarchus turned to the phenomenon of a lunar eclipse. During such an event, the moon passes through the shadow cast by the earth. This shadow, he reasoned, is a long cone stretching out into space away from the sun. By observing the moon's passage through this shadow cone, one could deduce information about the cone's width, and by extension, the size of the object casting it, the earth. Aristarchus introduced a crucial hypothesis based on observation that the diameter of the earth's shadow at the distance of the moon is twice the diameter of the moon. This observation, combined with the previously determined distance and size ratios, allowed him to construct an intricate geometric argument involving a series of similar triangles. These triangles connected the diameter of the Earth to the width of its shadow cone and the diameter of the Sun to the overall geometry of that cone's formation. Through a chain of propositions, he methodically unwound the relationships between the three bodies. His calculations ultimately yielded his final set of conclusions. The diameter of the Sun is between 6 and 7 times the diameter of the Earth, while the diameter of the moon is approximately 1/3 the diameter of the Earth. A complete, albeit flawed, model of the Earth-Moon-Sun system, with all its relative sizes and distances established through geometric proof, was now complete. The principal weakness of this monumental work, and the reason its numerical results are so far from modern values, lies in its foundational empirical measurement. The entire edifice of Aristarchus' cosmic ratios rests upon his measurement of the Sun-Earth-Moon angle at dichotomy as 87 degrees. The true value of this angle is approximately 89 degrees and 50 minutes. The geometric problem is exquisitely sensitive to this input. The difference between an 87-degree angle and a nearly 90-degree angle, while seemingly small, translates into an enormous change in the calculated distance ratio. The Sun is, in reality, nearly 400 times more distant than the moon, a factor 20 times greater than Aristarchus' result. Measuring this angle with the precision required was a task far beyond the capabilities of naked eye observation and ancient instrumentation. The fuzzy, ill-defined nature of the lunar terminator makes identifying the exact moment of dichotomy an exercise in heroic estimation. One can almost sympathize with the ancient astronomer, squinting at the half-moon, attempting to capture a fleeting geometric ideal with imperfect human senses. Yet, this spectacular failure is precisely what illuminates the work's genius. It forces a distinction between the logical integrity of the mathematical model and the contingent quality of the empirical data fed into it. The method was pure, sound, and beautiful. The measurement was fraught with practical difficulty. The legacy of Aristarchus is a legacy of method. The influence upon the sizes and distances rippled through the highest echelons of the ancient scientific community. The great Archimedes of Syracuse, in his own mind-bending treatise The Sand Reckoner, explicitly cites Aristarchus. While Archimedes' purpose was to calculate the number of grains of sand required to fill the cosmos, he used Aristarchus' figures and, more importantly, referenced Aristarchus' heliocentric hypothesis as a model for the universe. This reference confirms that Aristarchus' work was known, respected, and engaged with by the finest minds of the day. Subsequent astronomers, most notably Hipparchus of Nicaea and later Claudius Ptolemy, adopted the core geometric approach pioneered by Aristarchus. They dedicated their efforts to refining the observational parameters, seeking better values for the lunar parallax and the apparent diameters of the celestial bodies. They were his direct intellectual heirs in their commitment to a mathematical and quantitative astronomy, even as they ultimately rejected his most radical conclusion about the solar system's structure. It is impossible to disconnect the quantitative achievement upon the sizes and distances from the qualitative leap of the heliocentric theory. The realization, even with underestimated figures, that the Sun possessed a volume hundreds of times greater than the Earth supplies a powerful physical and aesthetic motivation for placing that colossal body at the center of the system. It feels incongruous for the giant to orbit the dwarf. The geometric proofs of this book provided the rational foundation for the heliocentric idea, a concept so far ahead of its time that it would wait nearly 2 millennia for its revival and eventual vindication. In conclusion, Aristarchus of Samos on the sizes and distances of the Sun and Moon is far more than a historical curiosity or a record of an ancient miscalculation. It is a landmark of human thought, a testament to a pivotal moment when the study of the cosmos began its long transition from mythology and philosophy to mathematical science. The work stands as a dual legacy. It was a specific, courageous, and deeply intelligent attempt to measure the world beyond our own more profoundly, it was a demonstration of a new way of knowing, a new kind of argument about the nature of reality. With geometry as his only guide and a handful of observations as his only anchor, Aristarchus sought to grasp the true scale of the heavens. He provided an intellectual paradigm, a method of cosmic triangulation, whose conceptual echoes would sound through the corridors of astronomy for centuries, from the Almagest of Ptolemy to the De Revolutionibus of Copernicus. It represents the audacious assertion that the human mind, through reason, and trace the outlines of the universe it inhabits,